Hi, everyone. We're going to be continuing with our discussion on the periodic table and periodicity. We're going to be talking about the trends in group 2. We're going to look at the ease of ionization of our group 2 elements, their reactivity with oxygen, water, and with dilute hydrochloric acid. We will also explain the trends in group 7, and we will consider the following properties, which are the physical state at room temperature, the strength of their oxidizing power, and we will discuss simple displacement reactions with chlorine, bromine, and iodine. We will also identify trends in period 3, the trends in which the elements change from metallic to semi-metallic. And we'll also be able to predict the properties of unknown elements based on their position in the periodic table. Okay, so let's get right into it. So in group 2, we have our alkaline earth metals. Okay, so our group 2 elements are beryllium, magnesium, calcium, strontium, barium, and radium. Most times we don't speak about radium because it is quite radioactive. So most times we do not include it in our discussion. So please note that all the elements in group 2 are placed in this group because they all have 2 electrons on their outer shell. All right, now our group 2 elements are not as reactive as group 1 elements. So our group 1 elements are known as our alkali metals. They are more reactive. And our group 2 elements are found in nature as compounds because they're very reactive. And as we stated before, they do have 2 electrons on their valence shell. And they have an unstable valence shell, meaning that they would want to lose those 2 electrons. Okay. Now, as discussed before, when you are looking at a group of metals, then you want to see that as you go down the group, you are adding more and more shells. And so the electrons, which are on the outer shell, which are the valence electrons. So here are the 2 electrons. So each element has 2 electrons on the outer shell. But as you will notice, as we go down, those 2 electrons are moving further and further away from the nucleus. So the nucleus is indicated by this dot in the middle, and the electrons are moving further and further away from the nucleus as we go down the group because the atoms are getting bigger. What it means is that going down the group, the number of shells increases and the outer electrons are being shielded from the positive charge of the nucleus, and the atomic radius increases and the first ionization energy decreases. So the first ionization energy would be the energy that would be required to remove an electron. And we're saying that it becomes easier and easier to remove an electron as we go down the group. So I want to just remind you of that fact, all right? So as we descend group 2, the metals become more reactive. As it becomes easier for the 2 electrons on the valence shell to be lost. So that means that we expect that all the elements will be able to do the same reactions, but we expect them to do them at different speeds. All right, so going back at the list of our group 2 elements, so we would expect that all the elements, beryllium, magnesium, calcium, strontium, barium, they should all be able to do the same reactions, right? So essentially, they can all do the same reactions, but at different speeds. Now, what you will find is that if magnesium is doing a reaction, you'll find that calcium does the same reaction, but calcium does it faster. Strontium will do it faster than calcium, barium will do it the fastest. So that's what we are going to be observing now as we look at the reactions of our group 2 elements. So our group 2 elements are able to react with water. So magnesium being the first one, which would be the least reactive in group 2, it doesn't really react with cold water. So if the water is cold, you will find it difficult for magnesium to react with the cold water. But if you convert that water into steam, you will find that magnesium burns vigorously with steam, and we get magnesium oxide being produced and hydrogen gas. Okay, and of course, we can always confirm the presence of hydrogen gas by checking with a lighted splint and listening for the pop sound with the hydrogen gas. Now, calcium would be more reactive than magnesium because calcium would be larger than magnesium, and it would be easier for calcium to lose its 2 electrons. So calcium gives us a moderately fast reaction with water, right? It doesn't need steam to react. It can react with liquid water, but look at the difference with what is going to be produced. So when calcium reacts with water, we produce calcium hydroxide and the hydrogen gas. So please note that magnesium gave us magnesium oxide, but calcium would give us the hydroxide of the metal and hydrogen gas. And of course, if you had reacted calcium with steam, it would be very vigorous and you would get calcium oxide and hydrogen gas. But you are mostly required to know the reaction with cold water. The only one that you need to know the reaction for with steam is magnesium, because magnesium doesn't really react with cold water. Now, strontium would react faster than the calcium, so it gives a vigorous or a brisk reaction. It also produces the hydroxide, which is strontium hydroxide and hydrogen gas. And then barium would be the fastest. It gives a very explosive, vigorous reaction to give us barium hydroxide and hydrogen gas. All right, so here I just have another table here, which summarizes how the elements do react with water. So we see that magnesium has to react with water in the gaseous state, meaning that it has to be steam for it to form the magnesium oxide and the hydrogen gas. Calcium, on the other hand, can react with the liquid water, 2 units or 2 moles of liquid water to produce calcium hydroxide and hydrogen gas. Now, strontium does the same thing to produce strontium hydroxide and hydrogen gas. Barium does the same thing. However, there's something I want you to note. Now, calcium hydroxide is not very soluble, so we can leave the state as being solid. Strontium hydroxide, however, is soluble, and so we should actually have it in the aqueous state, and barium hydroxide is also soluble. So this is something I want you to note. So as the group 2, as we descend group 2, right? So as we descend group 2, the elements become more reactive with water. I should say the elements react more briskly with water, right? So you will notice that the speed of the reaction increases and the solubility of the product also changes or increases. So that is something that will come up on your MCQs. So not only do we find that the elements react faster, but the product actually gets more and more soluble going down group 2. So there is a common question that is asked: what happens as group 2 elements react with water in terms of the rate? So yes, the rate increases, and they also ask you what else is different. The other thing that is different is that the solubility of the product changes, because here we had magnesium oxide to the top, which was insoluble. Then we had calcium hydroxide formed, which was also insoluble. But as we continued down, we got strontium hydroxide to be soluble in water, barium hydroxide to be soluble in water. So there is a change in the solubility of the product when we have the elements react with water, as well as there is a change in the speed of the reaction. All right, now how do these elements react with oxygen? They all can react with oxygen to form the oxides, okay? So notice you should use 2 units of the metal to react with 1 molecule of oxygen, and you form 2 units of the oxide of the metal, all right? Now, the reactions, of course, will be more brisk as we go down. So we expect that magnesium probably will be very brisk, calcium would more or less be explosive, strontium would be very violent and explosive, and barium would be even more violent and more explosive than how strontium would react with oxygen. All right. And you see that with strontium and barium, they can give you 2 types of oxides. You can get the oxide where the strontium has a +2 oxidation state, or you can get an oxide where the strontium has a +4 oxidation state, but this one is the more common one that you are expected to remember. All right, so as we go down group 2 and they react with water, we observe that the solubility of the products increases, and that means that the alkalinity increases. So these are all hydroxides, so they are alkaline, so therefore they have a pH greater than 7, but the pH of barium hydroxide would be greater than the pH of strontium hydroxide, because barium hydroxide is more soluble than strontium hydroxide, etc. So the alkalinity increases, and that's what it means. Okay, next we need to see how these group 2 elements react with acids. All right, so typically we should remember that metals react with acids to form salt and hydrogen gas. And when we say a salt, right, I just want to remind you from now, a salt is formed when the hydrogen ions in the acid is replaced by metal ions or by a metal ion. All right, so it might be one metal ion, it might be two, depending on what the formula of the salt will turn out to be. So for example here, if magnesium should react with hydrochloric acid, the magnesium will replace the hydrogen in the hydrochloric acid and we'll get magnesium chloride. Now the formula of the salt really depends on the charges of the ions. So being in group 2, when magnesium loses its 2 electrons, it will form a 2- charge and the chloride forms a -1. So when you have ions and the charges of the ions are not equal, then at that point you must do cross multiplication of your charges. So that's why we end up with this formula being magnesium chloride MgCl2. So in order to balance this equation, we would need to use 2 moles of the acid to react with 1 mole of magnesium. So here we have our salt and here we have our hydrogen. All right, the same thing would happen if magnesium reacts with sulfuric acid, we will get a salt and hydrogen gas. Now, of course, all the elements in group 2 would be expected to do the same reaction. So if I got calcium and reacted it with hydrochloric acid, I would expect the same thing. I would expect that I would form calcium chloride and I would form hydrogen gas. Now, the only difference is that this reaction would probably be described as being brisk, and this one here would be of a greater rate or a greater speed. So we would say that this one would be vigorous. Now, of course, if we go down and we should have strontium react with the acid, then it's going to be even more vigorous than how calcium reacted. So we're going to get our strontium chloride and our hydrogen gas, and we can say that this was very vigorous, right? So we want to indicate that we know that as we are going down, you are increasing the rate of the reactivity because it is easier for the elements to lose their outer electrons, right? So this would be very vigorous. And of course, now when barium comes along, it can do the same reaction with the hydrochloric acid, and it forms barium chloride and hydrogen gas. And this one, we would describe it as being violent, right? Because of course it will be of a greater speed than how the strontium reacted. So that would conclude our discussion of our group 2 elements and how they react. The essence is that when they react going down the group, the reaction becomes more brisk as the elements are getting bigger and bigger in size, and it's easier for them to lose their valence electrons. So now we're going to turn our attention to our group 7 elements, which are our halogens. And our halogens include fluorine, chlorine, bromine, iodine, and astatine. We usually don't really talk about astatine because also it is radioactive. But I want you to observe that as we go down group 7, the atoms are getting bigger and bigger in size as well, just as what we saw in group 2. However, in the case of the group 7 elements, which are non-metals, unlike our group 2 elements, which are metals, or non-metals get less and less reactive as they get bigger in size. So you will find that there is a decrease in reactivity as we go down group 7 because there is an increase in the atomic radius, right? There is an increase in the number of electron shells. And because the elements are getting bigger in size, it makes it very difficult for an electron to be attracted. So if I'm trying to attract an electron to the outer shell, I need the nucleus to help me to pull that electron in. But if this outer shell is getting further and further away from the nucleus, it makes it difficult for the nucleus to attract that electron, right? It's much easier for fluorine, which is very small, for the electron to be attracted to that outer shell, because the outer shell is very close to the nucleus, and so that positive force of the nucleus can be exerted on that outer shell better, and the electron can be attracted more easily. So the smaller the nonmetal is, the more reactive it is, all right, which is the opposite of what we saw with our metals. We also observed something going down group 7. We notice that there is an increase in the melting points and the boiling points of group 7 elements as we go down. And we also note that the color of the elements tend to get darker and darker as we go down group 7. So let us go ahead and try to explain what is happening. Now, the first thing I want to remind you of is that our group 7 elements do not exist by themselves as just one atom, right? So they don't really exist in nature as single atoms, they are diatomic. So you'll always find the two atoms joined together. So you'll have two atoms of fluorine joined together to create a fluorine molecule, two atoms of chlorine, two atoms of bromine, iodine, acetylene. So all the group 7 elements are diatomic. So you'll always find two atoms joined together. Now, as we go down the group, because the atoms themselves are getting bigger, it means the molecules are getting bigger as well. And as the molecules get bigger, the forces of attraction between the molecules will also get stronger and stronger. All right, so these all form simple molecules. And so if I were to show you another molecule, say for example, this represents a fluorine molecule right here. If I got another fluorine molecule and put it beside it, then there is going to be some weak forces of attraction between these two molecules. And this would be known as van der Waals forces, all right? Now, what we notice is that the strength of the van der Waals forces depend on the size of the atoms. So right now with the fluorine, it would be very weak because fluorine molecules are very small. But if I were to get iodine molecules, for example, so iodine molecules are much bigger. So they will have a much stronger force of attraction between the molecules than what we saw in the fluorine. So that is why the melting point of iodine is stronger, right, than the melting point of fluorine, because the molecules of iodine are stronger. Sorry, the molecules of iodine are bigger, and so the van der Waals forces are stronger. All right, so because of that increase in size, that explains why the elements have an increase in their melting and boiling points as we go down group 7. And it also explains why it is that they have a darkening in their color as we go down. So fluorine exists as a pale yellow gas, okay? Chlorine exists as a green gas. Bromine exists as a red-brown liquid. Iodine exists as a purple-black solid. So we would assume that acetylene is also a solid as well. Based on what we see, there is a trend as we go down group 7 to change from gas to liquid to solid, all right? And that is because the molecules are getting bigger and the van der Waals forces between the molecules are getting stronger. All right, so far we have learned that our group 7 elements, in terms of their physical properties, which are like melting point, boiling point, density, that increases as you go down the group because the molecules get bigger. However, when we talk about the chemical properties, which talks about how these elements react, we find that the reactivity decreases as we go down group 7 because the atoms are getting bigger. So here is another diagram to just illustrate that fluorine is more reactive than bromine because fluorine, right? Fluorine being the smallest one here would be easier. It would be easier for fluorine to attract electrons towards it. And remember that as a nonmetal, you are trying to attract electrons. So for fluorine, which is smaller, it's easier to attract electrons. It's much easier for fluorine than it is for chlorine because the outer shell for chlorine is further away from the nucleus. And for bromine, it is even further away because bromine is big. Iodine is even worse. All right, so we observe that the reactivity of nonmetals actually increases up the group, right, in an opposite direction to what we saw with the metals. All right, as it concerns our nonmetals, let me just write it here. So because our nonmetals gain electrons, we speak about their oxidizing power. So nonmetals gain electrons to be stable and thus are oxidizing agents. Now, what we would observe is that the oxidizing power decreases as we go down group 7, all right? So if I were to be looking at the oxidizing power, it would decrease as we go down, okay? Because as we go down, it's more difficult for them to gain electrons. So there is a decrease in the oxidizing power as we go down group 7. Now, if we understand this, then it makes it easier for us to understand displacement reactions, which are coming up next. So what we now know is that fluorine is a better oxidizing agent than chlorine, meaning fluorine is better able to attract electrons than chlorine. Chlorine is a better oxidizing agent than bromine, and bromine would be a better agent than iodine. Now, because of the decrease in the oxidizing power as we go down the group, then we are able to explain what happens when we talk about displacement reactions of halogens. So this is how it works. If a halogen is added to a solution of a compound containing a less reactive halogen, it will react with the compound and form a new one. This is called displacement. Let's look at it. If fluorine, so fluorine is the element here. If fluorine looks at a compound and sees chlorine in that compound, well, in the compound, the chlorine has a -1 charge. All right, so this means that it has an extra electron, right? So this chloride ion here, which is present in the compound, it has an extra electron because it has gained an extra electron and it now has a -1 charge. Now fluorine, because fluorine is higher up in the group, higher than chlorine, and has a stronger oxidizing power than chlorine, fluorine is able to take the electron away from that chloride ion and take it for itself. So fluorine can take the electron away from chloride, which is a less reactive halogen. So what happens is that fluorine ends up getting that extra electron that the chlorine had or the chloride ion had, and then fluorine ends up becoming an ion, and then chlorine has to come out of the compound and become just a regular element with a charge of 0. So it had a charge of -1 before, it has to now go down to a charge of 0. So what we saw is that the fluorine literally displaces the chloride, takes its place in the compound, and then chlorine comes out as an element. The good thing about these reactions is that there are color changes that will be associated with them. So we can actually say that, yes, the reaction took place when we see the color changes. So as said here, a more reactive halogen will always displace a less reactive halide, which is the halogen that has gained an electron from its compound in a solution. All right, so here we have a table which helps us to summarize the entire thing. So if chlorine is added to potassium chloride, we don't expect anything to happen because chlorine wouldn't necessarily be reacting with itself, so we wouldn't see any color changes. So notice that these compounds are colorless. So when you have like potassium chloride, potassium bromide, potassium iodide, they don't have any color, right? However, the halogens have color. So remember that the chlorine gas is green, right? Remember that bromine, as it says here, is an orange liquid. And remember that iodine, it can look brown or it can look purple, right? So the halogens have color, but when the halogens have gained an electron and they go into compounds, the compounds are colorless. All right, now, if we should add chlorine to a solution that has bromide in it, because chlorine is higher up in the group than bromine, the chlorine is able to steal the electrons away from the bromide ion, and a displacement reaction will occur. So when the bromide ion has had the electrons stolen from it by the chlorine, the bromine has to come out of the compound and go by itself to form an element. So when the bromine comes out, it will make the solution become orange. So here it is that we would probably start off with the solution looking colorless, but then we add chlorine to it, we notice it changes to a brown color because the chlorine has displaced the bromine. Chlorine could also do the same thing with iodine. If chlorine sees the iodide ion in a compound like potassium iodide, the chlorine can displace the iodine, right? So iodine has to come out as an element, chlorine takes its place, and chlorine goes into the compound. And we will see the color change because we'll see a brown solution being formed. Now, bromine is lower than chlorine, so bromine cannot react with a solution of chloride ions because bromine cannot displace chloride because bromine is lower than chlorine and its oxidizing power is lower than that of chlorine. Bromine wouldn't react with itself. However, bromine is higher than iodine in group 7, so bromine can displace iodine if it sees the iodide ion in a compound. So the bromine would push out the iodide ion, take its place, and the iodine has to come out. So we would see a change. We would see the solution changing from orange to brown. Iodine, unfortunately, which is at the bottom of group 7, cannot displace chlorine, it cannot displace bromine, and it won't necessarily react with itself. Of course, this table doesn't include fluorine, or had it included fluorine, fluorine could have displaced all of these three beneath it. All right, so this other table here actually includes the fluorine. So this is showing you what happens. So if fluorine gas sees its own ions, it's not going to react. But if fluorine gas sees chloride ions in a compound, it is going to displace it because it is the strongest oxidizing agent of group 7. So here you see the fluorine taking the electrons from the chloride ion. The fluoride ion is formed because the fluorine now has the electrons and the chlorine element has to be formed. And you would notice that the solution changes from probably pale yellow to green. Now, fluorine could do the same thing with bromide. Fluorine could displace bromide from its compounds. The fluoride ends up getting negatively charged. The bromine comes out as the orange or red-brown liquid. So you notice a change from pale yellow to orange. Then the fluorine could also displace the iodide ion, and you would notice the change from pale yellow to violet or to orange, well, brown really, brown or purple. All right, so, and you can see that the chlorine cannot displace fluoride. It won't react with itself, but it can displace the bromide. It can displace the iodide. Bromine cannot displace fluorine, cannot displace chloride. It won't react with itself, and it can only displace the iodine. Unfortunately, iodine cannot displace anybody because it's at the bottom of group 7 and it has the weakest oxidizing ability. So that concludes our discussion on the reactions of group 2 elements and the reactions of group 7 elements.